Welcome back to our next lesson from Grade 10 Chemistry following the Australian curriculum. Today we're looking at electron configuration. So have a look at the image on the screen there. Is a model of how we draw an atom. It's obviously not what it actually looks like, but just pause the video for a moment and see if you can work out what I've actually got depicted on the screen there. Hope you had a go at that. Obviously these guys around the outside here are our electrons. We have the little neutrons in there, and then we have two protons. And it's the protons that's the important thing that determines what an element is, because there's two of them there. Two protons is helium. So it's an atom of helium. The same stuff that you get in balloons and stuff at parties and things like that. On the screen there, I've left the dates blank deliberately because that's our sequence of what we're doing. We've done our experiment last week and all our data analysis. So now we're up to that bit with the red circle there, talking about electron configuration. If you look ahead there, in the coming weeks, you can see what's coming. So, what we're going to talk about is electron configuration. Why do we do this? Because when we learn about how electrons are arranged in an atom and how elements are arranged in the periodic table, or how we arrange them, you start to be able to understand why an element has a property and predict how it's going to behave in a reaction. And this is important for chemists because we want to use the knowledge that we have. That's what applied science is all about. Pure science is just studying the actual science of what there is, such as, oh, there's so many electrons in that particular atom. But applied science is, well, how do we use that information? If it hasn't got enough electrons, it's going to react with another atom that's got too many electrons and form a new compound. And this is the basis for all the chemical reactions that we do in industry in our everyday lives. That's the idea of why we're doing this. If we understand what's going on inside an atom, we can predict how a reaction is going to occur and how an atom is going to react and what it's going to form after it reacts. And we can use that knowledge to help us out in our lives. And where are we heading? Further into chemical reactions next week. So here's our objectives. We're going to do a bit of a review of some of the stuff you should have done in grade 9 science around the structure of an atom, atomic number and mass, and look at the Bohr models of atoms to show how electrons are arranged. Got a couple of videos there for you to stop and have a look at, other ones on YouTube that you can check out. Just some videos to kind of inspire you and get you interested into what we're doing this particular lesson. So back in grade 9, you would have seen this thing here, the periodic table, okay? Because it's in periods, or it's like those columns and rows on the table there, that we arrange the atoms, or all the elements that we know of, okay? Grade 9 science, you would have looked at the smallest particles being atoms themselves. There are subatomic particles within the nucleus and so on. You've got your protons and your neutrons, as I mentioned on the first slide there. You've got electrons zipping around the outside. We often describe them as orbiting around the nucleus, much like you see planets orbiting around the sun. It's not really what's going on, but it's a good enough analogy to explain how it's arranged. If you go further into grade 11 and 12 chemistry or grade 11 and 12 physics, you get to understand a bit more about the reaction side of things and how the electrons will arrange themselves in chemistry. And in physics, you go beyond that and look at what we actually are talking about when we talk about a proton, a neutron, an electron, and how they behave. There's a nice analogy there. If the nucleus is a nucleus of an atom, there's a few different ways of describing this. A good analogy is if an atom, a tiny little submicroscopic atom, is the size of like a footy oval, the nucleus could be anything from sort of a pea in the middle to maybe a cricket ball in the middle, and the electrons are like specks of sand, which would be right on the very edge of that oval. That's kind of a good analogy. What's in between the nucleus and the electrons? absolutely nothing. It is nothing in that space. It is mostly empty space, kind of like a vacuum. There is nothing between the nucleus and the electrons around the outside. So here's an example of one element that we've pulled out of the periodic table. This one's lithium. You can see he's written lithium there. His symbol is Li, and he's got the atomic number 3. All right, so that's what we're starting to sort of describe here. The atomic number indicates how many protons. In this case, it's a 3 because it's written there. If there's 2 protons or 4 protons, it's not lithium. It is lithium because it has 3 protons in its nucleus. Think of lithium as in battery technology that's being used these days. It's used in some medications and drugs and things like that as well, a whole variety of places. Now, neutrons, so they're the other particle in the nucleus. Most lithium has 4 neutrons. Sometimes there's 3, sometimes there's more, whatever. Okay, so if lithium has 3 protons, and then it has 4 neutrons, that's 7 subatomic particles. And if you round off its mass number there, 6.94, that's about 7. So why is its mass not actually 7 like we worked out there? It's because not every lithium atom has exactly 4 neutrons. Some of them, just a small number, have 3. That's what we refer to as an isotope. Same substance, it's still got 3 protons, but it's got a different number of neutrons, and that's an isotope. Now, electrons. So these are the guys zipping around the outside, a bit like the planets zip around the sun. The protons have a positive charge. So if there are 3 protons, that is 3 positive charges. So there must be 3 negative charges to balance that out, which means there will be 3 electrons. That little E with the minus symbol is our symbol for electrons. And that means that the 3 positive charges is balanced by the 3 negative charges, and it is electrically stable. Electrically means just the charges are balanced. So, pause the video, have a look at this one, and see what you can work out. Look at the questions there. What can you tell us about the subatomic particles in beryllium? There's 4 protons because its atomic number is 4. The mass number is about 9. So 4, let's write that again. 9 minus the 4 protons. So that is those 4 protons. This number here is this number here. 9 minus 4 is 5 neutrons. Because 4 plus 5 is 9 particles in the nucleus. Now, you can see that it's slightly over 9 because there's some decimal places there. So some atoms must have more neutrons, so they must have 6 neutrons. There's a few in there that have 6, most of them have 5 neutrons. Okay? Alright, so when we look at our periodic table, like this guy here, we can take out one of them. So if we take out that one there, that's carbon. Carbon has an atomic number of 6, so there must be 6 protons. It has a mass number of 12, so there must be 6 neutrons to make 12. Some of them have 7 neutrons, that's an isotope. Because there are 6 protons, there must be 6 electrons, and we draw them around the outside, and that's what we've drawn here. 1, 2, 3, 4, 5, 6 electrons around the outside. Notice we drew 2 in that first ring, and the next ring out, we drew the balance. That's just the sequence for how it's done, because there's a way these electrons actually arrange themselves. Today's images, by the way, are brought to you by Chuck Norris, one of the original tough guys. So when I say the electrons are arranged in certain ways, that brings us to the idea of electron shells. Okay, An electron shell is just like an orbit, much like you have Mercury has an orbit around the sun, Venus is the next planet out, has a different orbit a bit further out, Earth has its orbit a bit further out, Mars is a bit further out again, and so on through all the planets. We as chemists arrange the electrons in these sorts of electron shells, or orbitals, we sometimes called it. Orbitals. Now what you notice in this first one here is there is 2 electrons in that first one. This is a calcium. We know it's calcium because there are 20 protons, 20 neutrons. If you look at your periodic table and look along to the one that's got 20 protons, or atomic number of 20, that's calcium. Because there's 20 positive charges, 20 protons, there must be 20 negative charges to balance it. And what we've done is we've put 2 electrons in the first electron shell. And notice we've got 1, 2, 3, 4, 5, 6, 7, 8 in the next one. So we draw them in pairs because it's just a convention that the chemists often use. Right, and electrons tend to exist in pairs, and that's probably the easiest way to explain it. So there's 8 in the next one. You'll see in the third shell, there's another 8. So what have we got so far? So in the first shell, we had 2. In the second, we had 8. In the third, we had 8, if you count them on the screen there. How many have I got so far? Well, 2 plus 8 is 10, plus another 8 is 18. What do I need to get to? I need to get to 20, so there must be 2 more. So I need a fourth shell, and that has the last 2, which makes a total of 20 electrons, which balances the 20 protons. Okay, that's the convention for how we do it. You put 2 in the first energy level, and then you put 8 in the levels after that. It doesn't keep going like that forever and ever because it does change a little bit the bigger and bigger the atom gets. But for our purposes, 2 in the first level, then 8 in every level after that. Right, so now it's your turn to have a go. Have a look at this particular link on the screen here. If you need to pause it and write that down, do that. You've got to have you've got to give yourself some time to construct some atoms that are listed in there. Okay, if you should have an image on your screen when you finish, and you can take a screenshot of that as a record that you've built a few atoms. I would suggest you try doing at least 2 or 3 as a bare minimum effort. We have another sort of simulation here, which is this particular website. Check him out. All right, looks a lot like the PhET simulations that you see that a lot of the physics work is done from. Have a crack at that one too. Have a look at him. You can see that you can take, it is an activity where you get sort of the protons and the neutrons and the electrons, and you've got to physically place them in the actual atom where they belong. Once you have a go at that, there is this symbol game there, and there's a nice little other game at the end there as well. All right, this is the periodic table I keep referring to. So for example, the carbon that we had before is there. The helium back on the first slide is there. Calcium's in there. All right, people often look for the valuable stuff. There's silver, there's gold. All right, copper is somewhat valuable. But what you notice is that they're all in one column. All right, they're all in one group, as we call it. The periods are the sort of the rows across the table. The groups are the columns that run down the table. What do we know about these 3 things? Copper, silver, and gold. They're all metals, and they all behave in kind of similar ways, and that's the structure that's actually been determined here. Obviously, gold is more valuable than silver, but they tend to not be too reactive, although copper's a bit more reactive. Silver's a little bit reactive, and gold tends to be somewhat unreactive. But this particular group here starts with hydrogen, highly explosive, and everything else down that column reacts very, very quickly and releases lots of energy. And that's the way it's done. You'll notice down here we have uranium. Obviously, we all know uranium being radioactive. Everything up to that point is naturally occurring. Everything from here down we find naturally. Everything above that, every number above that, what's the numbers? 93, 94, and so on, gets to 103 over here, and then it goes back up here. There's a few more that have been added on here. All right. Everything above uranium is created in a laboratory. It is made by people in a laboratory, like scientists, smashing atoms together to make these bigger and bigger atoms. But they are so unstable, they generally don't last very long, usually a fraction of a second. Like some of these larger ones up here might only last hundredths of a second, if or less, before it actually breaks apart and decays through radioactive decay. When I was at school, sort of in the late 80s, early 90s, the periodic table finished somewhere around about here-ish, but nowadays it's being extended further and further because our understanding of how to create these bigger atoms is being extended, and we have better and better particle accelerators to do it, and better detectors to detect those atoms before they decay in a fraction of a second. But here on Earth, uranium is the point that all the naturally occurring elements stop at, and that's obviously radioactive. It's so big, the atom itself is so big in terms of its nuclear size, the size of its nucleus, and it breaks apart, and that is radioactive decay. All right, have a think about what you've learned today, and that brings us to the end of today's lesson. Thanks for coming.